Today I'm going to talk about physics, starting with some what I hope of relatively simple concepts, but I want to get right into the Big Bang and general relativity in one video. So we'll start by saying that the distance is equal to the speed times time. And I think almost everybody knows that. Anyone who drives a car, flies a plane, or sails a boat knows that the distance you travel is the speed times the time. I'm using d and s and t because that's the way I was taught when I was studying sailing. Distance is speed times time. Mathematician would tend to say that r is equal to the velocity times the time. Using lowercase because it's a variable, and using r because it's the radius of an orbit. And when you're talking about space from a physics point of view, from a cosmological point of view, you generally mean the radius of an orbit. So I'm using the ones, first of all, that are best known to people. Now, this does not define distance. This is very important to understand. This is not a way of saying, well, we want to know the distance, we multiply the speed with the time. These equations started as a means of defining, in this case, speed, because space existed before speed did, so to speak. It's more fundamental, and I'm going to get down to the fundamentals later. So you can say here that this says that the velocity is the rate of change of the distance with the time. So that's the way the equation would be used by a mathematician or physicist. This is the way most people understand it, but I'm using that to get started. So where did speed come from? Since speed is created by distance and time, but what causes speed? Well, speed is equal to the acceleration times the time. The mathematician would write that down, that the velocity is equal to the rate of change of distance. When you do that twice, when you differentiate that twice, you get the rate of change of distance for the rate of change of speed, or the rate of change of time. So that's per rate of change per unit of time, per unit of time. So that's that's the acceleration, not the velocity. The acceleration is that. The acceleration is that. So this is called the second derivative. That's called the first derivative. However, where does acceleration come from? Well, acceleration comes from force is equal to the mass times the acceleration. The acceleration is defined by this, that it is the rate of change of force for a change of mass. And so this again would be written in a similar differential equation there. So force is mass times acceleration. This was taught to us by Isaac Newton. So now where does force come from? Well, force is defined by energy is force times distance. In other words, force is the rate of change of energy with distance. So these are some equations that we should know. That's right, that defines acceleration. Force is mass times acceleration, and energy is force times distance. Now, what I want the reason I'm doing this is that we think, well, okay, from the distance we can get down to find the energy. Now, the way that it really works in nature is that energy was created first, and that this rate of change of energy produced force, and that force produced acceleration. Acceleration produced speed, and speed produced distance. Now, let's see what I've got to talk about next. What I want to go into next is to say that I wrote a few notes here. Can't read them. Now, what I want to do is to show you how these were all created in the first place. And what was created first was energy, not space or time or acceleration or force or mass. Those came along later. Energy was the first to be created. And I'm going to here tell you that I think that this all started with the Big Bang, and that the best description you'll find anywhere, the most concise, precise, and interesting, poetic description of the Big Bang you'll find in the first 2 or 3 verses of the Bible, where you had, first of all, what we now call a singularity, or I think that's what it's called, which is a dot, except that it has no size and it has no properties. It is just a dot. And in the Bible it's described so well as without form and void. The earth, which really means the whole of the mass of the universe, was created, and it was without form and void, meaning it had no shape and occupied no space. So that's exactly how scientists believe that the universe started. And then what happened to it was that it was made to explode, if you like, by separating it in using energy. And that is described again very, very simply by the words, "Let there be light," which is energy in its purest form. And what happened was that nothingness, because that's really nothing if you consider that it had no size or shape, was divided up into, not, I won't say smaller, because you can't have anything smaller than nothing. But you can have multiple versions of it that are all separated at the speed of light. Velocity equals c. And this is what how the universe started. And since things are now moving, you've got time, because it takes time to move things. They don't go at an infinite speed, a very high speed, but it does take time. So that time was created, and as you see, they're separated now, and that formed space. So they're moving in what we call space. That's the space between the units of matter. And I should point out that they're going not just in 2 directions like this, but in 3 directions. Now, why 3 directions? That's very interesting. I will only describe it very briefly. But if you have only 1 dimension of space, you can only have 2 bodies separated. Because if you add another body, it now gives interference between its relation with that. The space between there and there has to go through that one. And so you've got 2 spaces, and you can't, this one can't have a force on this one because this one's in the way. Even though it has no size, these lines have no cross-sectional area. So to get more than 2, you need 2 dimensions of space. But with 2 dimensions of space, you can only have 4 bodies in 2 dimensions of space. There's nowhere to put a 5th where it can get a relationship with the others without interference. So you need 3 dimensions. So you've got 1, 2, and 3, and then have another one out here, another one out here, and now there is no limit to the number of units you can have. So 1 is not enough, 2 is not enough, 3 is enough. And I rather think that nature adds up this way: 1, 2, and enough. So that's why we have 3 dimensions of space. Now, I now want to start to talk about these separations as to how they're related to energy. And I'm going to get into Einstein's area now. We're going to leave Newton's area and get into Einstein's. And we're going to talk about, and I'll talk about the Earth and the Moon. If that's the Earth, then because of this momentum, oh, I should point this out, I forgot to do so earlier, that when I was describing that energy is equal to force times distance, I should point out that that P, which stands not for potential, P stands for momentum, is equal to force times time. It's also equal to mass times volume, and energy is equal to mass times the volume squared. That's the dimensions. There's a half in there. The half is there because the energy is created when a body is accelerated, and if it's accelerated at a constant rate, it has an average velocity of half the final velocity, and that's where that half comes from. So that energy has that. These are the two equations we use more often for momentum and for energy, but I'm using them this way because I want to show how they're related to force. And there's a very little difference between force times time and force times distance, and that's the association between energy and momentum. And this is what is important. At the Big Bang, both of these were created. Energy, because that's what enabled the mass or matter to expand or separate, and momentum because once it started it couldn't stop. And so there's what they call conservation that came with the Big Bang, and everything has exactly the same momentum as it had when it started, and the same energy. So we're now going to see how this relates to cosmology now, and to Einstein's general, both of his theories on relativity. So we'll take the Earth as moving through time. Now, I say through time, it's moving. And if it's moving, the only way that it moves absolutely, that is to say, it's not relative, it's absolute, is as it goes through time at the speed of light. And so does the Moon go through time at the speed of light. But the Moon, when it left the Earth, not now, but when it left the Earth, it was going away from the Earth, like this. And this is time, and this is space. So the Moon was going away like that, and that's the Moon's time dimension. This is the Earth's time dimension. And you'll see that it's going in a straight line if it is travelling at a constant speed. But it's not, and it was pretty much when it started, but it slowed down because of gravity. I'm not going to talk about gravity. But that's what happened. But now I'm going to say, okay, let's take something, take this or anything you like to take. Take the, now, this is movement of the Moon relative to the Earth. Now I'm going to talk right down to Earth, and this was the kind of thing that Newton could do too. He could watch the Moon, and he could throw something in the air and catch it, or drop it on the floor. And what happens there, however, you'll notice, is that if I take something and throw it up, it doesn't keep going. The momentum doesn't keep it going upwards because of gravity. And as I say, I'm not going to explain gravity. But instead of that, if I throw that ball up, it goes up and it comes down. And so we say, why does it come down when it has momentum to keep going in a straight line? And here Einstein said, then it must be then that since it keeps going at a constant speed through space, space must be curved. So we've got as far as general relativity, where Einstein said space is curved so that when you throw something up in the air, the Moon too, by the way, although it went up like that, would eventually come back, and much longer. But I'm going to point out something else, and that is that I'm showing these curves pretty sharp because I want to get them on this board. But the scale is not very good, because when I threw that up, it went up in about, and down again in about a tenth of a second. So that might be, in space, that might be, it only went up, let's say it went up 2 feet. That's the distance in space that the pillbox went when I threw it. How much time was involved? Well, it was about, shall we say a tenth of a second? But this is distance and this is time. So we've got to get them on the same kind of units to be able to get some meaning from it. So this is the distance through time, and that distance is equal to the speed of light times the time. So it's 1/10 of a second times 186,000 miles per second. So it's that times the number of feet in a mile, which is 5280. So you see that now is the length of this line, and as you can see, it's very, very long. So this line is squashed a lot to show the curve. In fact, you wouldn't be able to see the curve. And I say that because I'm going to say that this arrives back actually at about the same time as that. If you were to flatten this down both and take the whole lot as far as this, a tenth of a second, I think something seems to be wrong with that. It looks rather large. 186,000 miles a second. Oh, it's a tenth of a second. Okay, so it's 500 times. Now, it still seems to be a long way. But in any case, it's a very, very long. And when you flatten that out, then this it does not rise very much. And they're pretty much the same. So that when I throw this up and bring it down, it comes down at the same time as far as we're concerned. But if something is traveling much faster, and this is shorter, so it really does a curve like that, you see here we've lost some time if it comes down here. And this is called time dilation, and that's one of the things that we learn about in relativity. I've gone far enough, I think, because I got as far as the Big Bang and relativity, and I started by talking about knowing that if you drive a car a certain speed for a certain time, it goes a certain distance. So that, I think, is a short lesson in cosmology. Thank you for watching.